Welcome back to part number 3 about parsers. We have defined some very simple parsers. Then we developed in the second part a few parsers to kind of parse several, use several parsers in a row. And even though the parsers that we have defined are very primitive, they are already powerful enough to parse arithmetic expressions that have deep structure. And that's what we're going to do in this last part of this lecture on parsing. Here is the expressions that we're going to parse. Then we want to have simple expressions that are built from simple digits with addition and multiplication. Expression can be parenthesized, and moreover, we want times to bind stronger than plus, and we want both of them to associate to the right. So what does that mean? If we have a plus b plus c, we want to parse that as a plus open paren b plus c, and if we have a plus b times c, we want to parse that as a plus b times c. All right? So this is fairly conventional, just arithmetic expressions. So how are we going to implement this using those very, very simple parsers that we defined in the previous 2 sections? Well, the first thing that we're going to do is we're going to write down a grammar for these expressions. And if you've taken a course in compilers or formal languages, or you look in any programming language definition in the back where the grammar of the language is defined, you will find a grammar that looks very similar to this. So there's an expression, there's a term, there's a factor, and these 3 productions are used to encode the binding of the expressions and the kind of, the fact that these are defined like this in this recursive form encodes the associativity. So an expression is a term plus an expression, or a term is a factor times a term, or a factor, and a factor is a digit or a parenthesized expression, and a digit is, well, a digit. All right, so that's where the recursion bottoms out. But as I said, this is real standard encoding of expressions in a grammar. Now, what we're going to do is we're going to massage this grammar a little bit. And again, it's also very common. Every book on compilers will do this, and often grammars are defined like this. So the way we'll do it is saying, an expression is a term followed by plus and an expression, or the empty string, or epsilon. This is the empty parser that doesn't kind of recognize anything. And then term is a factor, and then followed by star term, or again, the parser that only recognizes the empty input. Okay? So if we take this, we can now immediately translate this definition here, which is recursive here. You see, an expression is defined in terms of an expression, but there's first a term, and then it recognizes the plus. So you see here, expression recognizes a term, then a plus, and then an expression, and then it returns the expression plus the term plus the expression, and then this one is the empty case. All right, so you will immediately return the term. And the same for term, and the same for factor. So in some sense, that encoding of the grammar has a one-to-one correspondence with this recursive expression here. And that's the nice thing. So in some sense, these parser combinators, as they're called, are like an internal DSL. So instead of writing a grammar in some externally defined language, like Yak and Lex, compiling that into another language, we can do this all within Haskell and then use all the facilities of Haskell to define helper functions and so on. And parsers are one of, I think, the most elegant, internal DSLs that you can imagine. And as I said, you can do very sophisticated parsers, and you can push this idea pretty far. Now, the next thing is we're going to define an evaluator that takes a string, parses tries to parse the string as an expression, and then return the resulting value. And if we go back here, you see that we're already evaluating the expression as we're parsing it, because we're parsing the plus operator, and then we're taking the term and we're adding the result of parsing the expression. So the result of this is already a parser of int. So instead of, we're not even creating a parse tree, we're immediately, as we're parsing, we're evaluating the expression. So that's what you see here. We parse the expression, given the input. Since this returns either an empty list or a singleton list, if it returns a singleton list, we take the head, so we take that value. We take the first element, which was the number, and then there's the rest of the string. If this fails to parse, the head will throw an error, and this whole thing will fail. So let's see here. If we're parsing 2 times 3 plus 4, that should return 2 times 3 is 6, plus 4 is 10. And guess what? That's the value we get. And if we're evaluating 2 times 3 plus 4, what we should get is 3 plus 4 is 7, times 2 is 14. Guess what? It behaves as expected. Okay. In the exercises, you will do several things with parsers. And in particular, one of the things that you will do is you will have to implement the sequencing operator that we used but didn't define. So we have defined various operators on parsers, but one of the essential ones, the sequential composition, we didn't define, and that's the main exercise of this week. So happy hacking, make sure you do your homework, and see you next week. Bye-bye.